Hello everyone, and welcome back. Today we're going to continue our exploration of multiple linear regression and focus a bit more on the explanatory and predictor variables in that particular model to see, for example, whether one or more variables are not really contributing to the accuracy of the model, or to investigate whether one variable is interacting with another, or possibly if there's another variable not in our model that we may want to potentially add to our model for accuracy. So the first concept that I want to introduce is what is referred to as confounding. So confounding exists when there is a meaningfully different observations on the response vector y that results from introducing extraneous variables to our model. So let's assume that, for example, we are trying to model the happiness for a particular individual. And let's assume that our model is of the form beta 0 plus beta 1 x, which corresponds to age, and then beta 2 then x, which corresponds to the health of that individual. And let's assume that this is what we refer to as our base model. So this is our hypothesis in terms of that we can accurately represent or model happiness linearly with respect to only age and health. So these variables are what we refer to as our explanatory variables. Okay? But it's possible that we introduce new variables to our model that we don't originally hypothesize. For example, somebody else may conjecture that other variables may be contributing to happiness. For example, some people may want to consider, for example, a new variable x, which is sleep, or possibly many others into this model. So these are not, of course, from our base model. These are extra variables, or moreover extraneous variables. So these are what we refer to as our extraneous variables there. And obviously we should not forget our lonely little residual term at the end. So regardless if it is explanatory or extraneous predictors, if you plan to build a model from them, then all of these are our predictor variables, right? So either these predictor variables could be numerical, we've already discussed that, or they could be categorical, or a mixture of them, right? Because if we're working with categoricals, we can introduce, for example, dummy variables and binary coding in order to code them into this regression model. So one question that we need to ask is, well, for example, does introducing these new extraneous variables give us meaningfully different observations? So obviously a couple metrics that some people use is, for example, the R-squared value. And if you don't remember, the R-squared value is 1 minus SSE divided by the SST. And one of the downsides of the R-squared value is that as the number of predictors P increases, then the R-squared value will theoretically, not necessarily strictly monotonically increase, but monotonically increase to 1, even if the extraneous variables for which we're introducing into our model are not really contributing meaningfully different observations on a response variable y. So obviously an alternative for the R-squared, in case you don't already know, is the R-squared adjusted value, which is 1 minus the MSE divided by the MST, right? Now, some people will desire that the R-squared value goes to 1 because some people will believe that that implies that your model is good, right? So obviously, what is the downsides of that? Well, the f-test statistic we know is going to be equal to the MSM divided by the MSE, which is just the same thing as the SSE divided by n minus p minus 1. And obviously, as p goes to infinity, the SSE also goes to 0 simultaneously. So n minus p minus 1 for a fixed sample size n will go to infinity, SSE will go to 0, and this obviously is going to go to infinity as you increase the number of predictors. So if that goes to positive infinity, that means we have more and more evidence to reject The null hypothesis that beta 1 is equal to beta 2 is equal to all the way down to the last predictor are all equal to 0, implying that our model is appropriate. But of course, this can be very misleading because this is just a theoretical function of these particular formulas, right? And this obviously creates the issue of what we refer to as overfitting, which you definitely should avoid. So an alternative that you can do, for example, to see whether your true model is actually better or worse with the one or more extraneous variables added or potentially removed if you originally added them, is what is referred to as a partial f-test, which we won't review here, right? But the partial f-test allows us to see if one or more variables added to our model is better than the original model before we added them, right? Or if a full model is better if we reduce it by removing them. Right. So another issue that we get when we start removing variables, which is sort of the opposite of adding extraneous variables, is what is known as omitted variable bias, which some people just abbreviate as OVB. And that's the bias associated to co-allocating the effect of the removed variables to the variables that remain into our model. Because, for example, if we have x1, x2, and x3, and x4, and we decide that x4 is not contributing to our model, then the beta coefficient value associated to, for example, beta 4 needs to be allocated to the coefficients of x1, 2, 3, and also our lonely little intercept in the front. So if x4 truly is suitable for that model and you remove it, it's going to conflate into the other coefficients, which may undoubtedly tell you that those coefficients are actually better when you remove that x4 variable, right? Which obviously can give you a lot of misinterpretations. So one can view, for example, omitted variable bias as sort of the opposite consequence of overfitting when you start talking about adding or removing predictors in your model. Another concept that is very closely related to confounding is what is referred to as interaction. An interaction exists if the values of your response variable y vary significantly at different values or levels of the predictor variables or variables in your base model, potentially due to the explanatory or extraneous variables interacting with one another. Obviously, if you have extraneous variables that are interacting with either other explanatory or extraneous variables or your explanatory variables, it's really hard to test that, especially if you do not know exactly what those extraneous variables are that you possibly want to or should include in your model. Let's assume that we want to, for example, model happiness and age, and you sample across these two variables, and this is the data that you get. Obviously, you can fit a linear model to this data. That's not a big deal because technically you can fit a linear model to any data set, even if it's not appropriate. But if you sort of look closely at what we're looking at here and sort of partition this into, for example, these three regions here, where if you were to build, say, confidence and prediction bands around each of them, you would see that, for example, a good prediction band or confidence band would be that one. Another prediction band would be that one, which is obviously larger, and the prediction band for this region would probably be more appropriate for that, with a couple outliers sort of hanging around outside of those bands, which is common, especially for large data sets when the variance is large, right? So one could ask, okay, well, obviously, there's these three levels across our age spectrum for which the values of our happiness is significantly different. So, for example, let's assume that this is 18 and 35 years old, respectively. So one could ask, okay, well, what's sort of going on at the age of 18 for which the variance obviously appears to be a lot larger, still increasing, and you have a couple people that potentially, decreased in terms of happiness, but what sort of is going on there? And you can, for example, conjecture, okay, maybe going to college or university is contributing to that first shift, so maybe college whether it be how many years you've gone to college, so that would be a numerical, or how many, what's your classification in college, so a categorical representation, may or should be included into your model. And you can ask, okay, well, what's going on at the age of 35? Well, obviously by then maybe you've finished college or maybe not, but maybe that's when your career starts to stabilize, or maybe that's when you decide to get married or have children or whatnot, for which maybe, then your happiness starts to quote unquote stabilize, i.e., it pretty much stabilizes around the same exact value for most individuals, right? So you could consider these extraneous variables, whatever they may be, include them in your model and actually see if they're actually contributing to that change, i.e., college is interacting with age, or college is interacting with happiness, college and age is interacting with happiness, and so on. So, if that's the case, so let's assume that, for example, your original model is beta 0 plus beta 1x age for our base model. Maybe we can introduce a couple other variables into this model. For example, we can build a new model. For example, y is equal to beta 0 plus alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 plus epsilon, where these alphas obviously are different from the original betas, where, for example, x1 is equal to x if, let's assume that that original age variable is x, if x, for example, belongs to the age range of 0 to 18 and 0 otherwise, we can say that x2 is going to be equal to x if x belongs to the category range of age 18 to 35 and 0 otherwise. And then x3 can be defined to be equal to x if x belongs to the interval 35 to infinity for age and 0 otherwise, right? And that, although we're not exactly sure what's triggering those changes, college, career, or marriage, at least that creates these three different levels, and then we can start to conjecture of what exactly this variable, x1, x2, x3, and so on, actually are representing. Now, let's consider the case where you actually have two predictors in your model. Let's assume that they have the variable coefficients beta 1, x1, and beta 2, x2, right? And you want to ask whether x1 and x2 appear to be interacting with each other. So let's assume that, for example, you make one of these variables the variable for which you're going to make constant at some particular values, right? So let's assume, for example, y is equal to beta 0 plus beta 1 x1 plus beta 2 times a particular constant. For example, let's call that constant c. Obviously, beta 0 and beta 2c are both constants, so if you were to change this value of c, then if you look at our curves with y on the vertical axis and x1 on the horizontal axis, for different values of c, for example, c1, C2 and C3, they're just going to be vertical shifts of each other. So if you ever see something like this, which we usually refer to as response curves, this would imply that x1 and x2 do not appear to have any interaction. But if there is an interaction between x1 and x2, so if x1 and x2 have interaction, then that means an appropriate model would be, for example, y is equal to alpha 0 plus alpha 1 x1 plus alpha 2 x2 plus gamma 1 2 x1 x2 plus epsilon, i.e. you would include an interaction term at the very end. And obviously, if you change around the values of x2 and sample across x1 and y, what you're going to see, if there truly is an interaction, for example, if that's C1, obviously it may be sometimes parallel, But those curves, those response curves, likely are going to cross. So in this type of scenario, if you do not exactly know if there's an interaction, what you can do is you can construct a bunch of response curves for your two or more variables and plot against the y in the two-dimensional plane and sort of see if those response curves cross. If you see that those curves definitely do cross and those curves are definitely not parallel to one another, then you probably should be including this interaction term inside of your regression model and hence implying that you believe that there is interaction between your predictor variables. Now that we've discussed confounding, which analyzes y across different values of x, an interaction, which discusses whether our predictor variables are interacting with one another. Now we get to what is called collinearity, which of course is going to share a nice connection with interaction. So collinearity exists when there appears to be a large correlation between your predictor variables. Obviously, there should be a correlation between your predictor and response variables, else you wouldn't be building a linear or polynomial regression model between those two, right? But the issue is when there is a correlation between your predictor variables, i.e. they appear to be dependent on one another, right? Which obviously if there is interaction, there will be dependence. So let's just list out a couple things that we definitely usually want. So ideally, we want the covariance between a response vector y and our predictor vectors xj, where j ranges from 1 to p. And some people will also abbreviate this as sigma squared y comma xj as the variance between y and xj, which is just a fancy way of saying the covariance between them. We typically want this to be large, i.e. the correlation between them to be close to plus or minus 1, or the multiple coefficient of determination to be close to positive 1. So that's the first thing that we typically want, and we typically want the covariance between xj and xk, which is equivalently written as sigma squared of xj comma xk. We typically want this to be small, and ideally the closer to 0, the better. Right? So in order to quantify all of our coefficients, usually we construct what is referred to as a correlation matrix. So a correlation matrix is definitely one of the easiest things you can construct, and definitely you should, if you want to investigate the multicollinearity between your response and your predictor variables. So the correlation matrix has the following structure. So obviously it is going to be a matrix, and I'm going to write the labels of each of the rows and columns as follows. So we're going to have y, x1, x2, all the way down to xp along the rows. And we're going to have y, x1, x2, all the way down to xp along the columns. So let's draw this nicely and nice and neatly. So this is going to be our correlation matrix, right? So obviously the correlation between a variable and itself are always going to be equal to 1. So it's trivial that the diagonal entries of the correlation matrix are always going to be equal to 1. And you should know that the covariance between a variable AB is always equal to the covariance between BA. So this matrix is obviously going to be a symmetric matrix, so there's technically no need to calculate one side of this matrix. So let's assume that we would just want to focus on the upper triangular portion of this matrix. So, what do we usually want for the correlation between y and x1 through xp? Obviously, if you see 0.98, that's obviously a good sign. If you see negative 0.86, that's a good sign too. It's just in the opposite direction. So beta 1 is probably going to be positive, beta 2 is probably going to be negative, and if that's 0.91, then beta p should be a positive number as well. Agreed? So if we look at the other values in this matrix, we hope these are low. So for example, if you see something like 0.01, that's a good thing. If you see 0.13, that's a good thing too. But if you see like negative 0.94, that's a bad thing, right? So this is going to be your correlation matrix, right? So that's obviously bad, and those two are good. Closer to 0, the better for the predictors, higher and closer to plus or minus 1 for the response and a predictor, good. Right, so that's the correlation matrix. And you can also R squared, find the R squared matrix, and you can have a similar equivalent interpretation for that matrix. Now, I just want to make a quick note on multicollinearity or collinearity, because multicollinearity can come in one of two forms. The first is data-based multicollinearity, which is associated to the correlation matrix because we're focused on our data. But keep in mind there is a second type of multicollinearity which is referred to as structural multicollinearity, which is where you have, for example, in polynomial regression, we have, for example, x and x squared. So obviously as x increases, x squared increases, so that's going to be a positive correlation between x1 and our second variable x2, right? So polynomial has structural multicollinearity. You could also have structural multicollinearity when you start including interaction terms, which also exist in polynomial, and also just basic regression, and also sometimes when you introduce dummy variables. So that's when you have, for example, x1 times x2 and the variable, for example, x1, because obviously as x1 increases, the product x1 times x2 is either going to increase or decrease depending on the sign of x2. So keep in mind, there are these two types of multicollinearity. The correlation matrix is just focused on the data-based version of multicollinearity, and obviously you should have your own tools for dealing with structural multicollinearity, such as predictor standardization. A nice numerical metric that you can use to determine whether there appears to be some interaction or multicollinearity associated to a particular predictor variable is known as what is the variance inflation factor, or VIF for short. So recall that the variance for the model coefficient beta hat k is equal to the homosedasticity variance sigma squared times the kth diagonal entry of the matrix xtx inverse, right? And we've already proved this before. But one can show that an equivalent way of writing this is the following. In particular, the homosedasticity variance times 1 divided by n minus 1 times the variance of that random variable xk times this strange looking term at the end, 1 minus 1 divided by 1 minus r squared k. So this term here is what we're going to represent as VK, or the kth variation inflation factor. So the kth variation inflation factor, right? Or variance inflation factor is what some people say as well. Now, one can ask, well, what is this r squared k value? So r squared k is the r squared, the multiple correlation coefficient value for the model xk, the variable that is being observed, equals alpha 0 plus alpha 1 x1 plus alpha 2 x2 all the way out to alpha k minus 1 xk minus 1 plus alpha k plus 1 xk plus 1 plus all the way down to alpha p xp plus epsilon. So notice that this is practically our full model on the right hand side, but it's all except for the xk beta k term. right? And instead of regressing y against our predictors, we're regressing the variable under consideration against all of those, right? And that r squared value is what we call this fancy r squared k value, right? So the variance inflation factor is given by this term, right? So Vk is equal to 1 minus r squared k, where r squared is that regressor r squared value where you regress xk against all of the values except for xk. So xk is regressed against, I'm going to write it as everything except for the complement of xk, right? So a couple little mathematical things you should notice. One, the variance inflation factor is going to be equal to 1 if r squared k is equal to 0. So what does r squared k equal to 0 mean? So that means xk is not linearly correlated with all of the variables aside from xk, right? And notice we're not talking about y here. That's for other things, right? We're trying to see if one variable is interacting with another. So this means that xk is not linearly associated to the other variables in the model, which I'm just again going to represent as xkc, xk complement. And the other extreme is where the variance inflation factor obviously is equal to positive infinity, and this occurs obviously when r squared k is equal to 1, and this occurs when xk is or is strongly linearly associated to xkc. Now you have to keep in mind, just because it's linearly associated to xkc, it could be linearly related to just one of them, two of them, all of them, or a proper subset of them, bigger than 5 or something like that. So obviously you could do, for example, a partial f-test to look at that in a little bit more closely. Now, the variance inflation factor is in the unit of variance because that's in the formula for the variance of beta hat k. So to have a better interpretation or feel for this metric, we introduce another metric which is called the multicollinearity index. The multicollinearity index, which are going to be represented as kappa j, which will be equal to the square root of the variance inflation factor, Vj. So that's obviously going to be equal to 1 divided by the square root of 1 minus r squared k. And obviously this is going to be an element from 1 to infinity. So just as a rule of thumb, typically if the multicollinearity index kappa j is greater than or equal to 5, and 5 obviously is a subjective number, typically that's what you refer to as large. And obviously this 5 can be viewed as a normally distributed number. So you could, for example, do 3. That's a common benchmark number. You could do 7. You could do 10. But keep in mind, the smaller the data set you have, you should be a little bit less strict with those numbers to avoid any bias in your interpretations. The last quantitative metric that we're going to look at today is what is known as added variable plots, and it helps us answer the question, does a particular predictor contribute meaningfully to our regression model? So if you're considering removing a variable completely to minimize the potential of having omitted variable bias, one of the first things that you definitely should look at is the added variable plot for that predictor. So if that xj contributes meaningfully to a regression model, then a couple things will be true. If it is the case that it is contributing meaningfully, then r hat, which I'm going to represent as the standardized residuals for the model y regressed against x1, x2, down to, for example, xj minus 1, xj plus 1, all the way down to xp, or equivalently, everything except for xj, will be dramatically affected or different from the r hat values for the model xj regressed against x1, x2, down to xj minus 1, xj plus 1, down to xp, or equivalently, xjc. So what exactly are we looking at here? So if we just remove the predictor xj from our model and regress y against it, we're going to have some standardized residuals, and emphasis on standardized, right? Because the residuals by themselves can be misleading if interpreted correctly, especially on the tails of the distribution of the predictor values. So if you look at the standardized residual values when you remove xj, and you look at the standardized residuals for the model when you regress xj against all of its counterparts, and they are about the same, what does that exactly mean? Well, notice that the models on the left-hand side of this regression is the same exact thing. So if they are the same, that implies that there exists a nice and beautiful, meaningful linear regression between y and xj, implying that xj has a meaningful contribution to the story of y. So if that is the case, if you plot the standardized residuals against each other, what will you get? So for example, here's one scenario. Let's assume that this is xj regressed against everything except for xj. And let's assume that this is y regressed against everything except for xj. And you plot the standardized residuals against each other, then you should get a line if there is a meaningful contribution between them. Now that's not the only scenario that you could have, but if you listen to least to greatest, you definitely should get something like that. Again, let's assume that we regress xj against xjc, and again, y regressed against xjc, and then keep in mind that these points are the standardized residuals for each of them. So this is the standardized residuals for that model, this is the standardized residuals for that model, and so on, right? So obviously it could be the case where these points are closely related, but in a negative fashion. That's perfectly okay too. So if you see any one of these plots, which are known as added variable plots, which plot the standardized residuals for each of these models, then this first model can be interpreted as the following. In particular, we have evidence to believe that the beta j constant is positive, therefore it should remain in the model. If you get a line that's similar to that, that means we have evidence to believe that beta j is negative. And obviously positive nor negative is perfectly okay because the t-test tests against the value of the coefficient being equal to 0. So if you get an added variable plot that looks like this, where again this is xj regressed against xjc and y regressed against xjc, the standardized residuals of each, and you were to get, for example, this type of plot, and you were to fit a, for example, a simple linear regression line, and you were to sort of get something like that, then obviously we have evidence to believe that beta j is equal to 0, and hence you might want to consider removing that variable xj from your model, right? And obviously how large is large and how close is close to 0. Keep in mind all of these models have the form, let's call it, for example, L is equal to alpha 0 plus alpha 1. I don't know, R1, where R1 is the slope of, or alpha 1 is the slope of that particular line, right? So obviously that's going to be your slope, and you can, see, is it close to 0? Is it significantly far from 0? So the null hypothesis here is that, alpha 1 is equal to 0, and if you want to prove that it's either significantly positive or significantly negative, then obviously the goal would be to reject the null hypothesis, which would imply that you would keep that variable xj into your model. But those are some of the basics that you definitely should have in the back of your toolkit when you are considering adding, removing, or just analyzing your variables as a whole when you're working with a multiple or polynomial regression model. Hope you enjoyed this video, and I'll see you in the next one. Take care.